Today we are going to start a very important operator, or you may say a class of operator which, are, which has great importance in quantum mechanics. This class of operators are known as Hermitian operators. First of all, we will define Hermitian operator and then we will discuss its important properties, and after that some of the important problems based on these operators. So to define the operator, Hermitian operator, let us consider two well-behaved eigenfunctions, or you may say Eigenkets. Let psi1 of x and psi2 of x are two well-behaved eigenfunctions vanishing at infinity. This is a most important property of these functions, that these functions will vanish, will become zero at infinity, that is either plus infinity or minus infinity. Both of these eigenfunctions become zero. And we also consider an operator A hat be an operator. Psi1 of x and psi2 of x are two well-behaved eigenfunctions which vanish at infinity, and we consider A hat is an operator. Now this operator A hat will be called a Hermitian operator when it will satisfy a condition which I am just writing down here. So A hat is called a Hermitian operator. Hermitian operator if, what is the condition? The condition is Bra A hat psi1 Ket psi2 is equal to Bra psi1 A hat psi2. If the operator A satisfies this very condition, then we call it a Hermitian operator. It means the scalar product of A psi1 and psi2 is same as the scalar product of psi1 with A psi2. If this condition is satisfied, then the operator A is known as Hermitian operator. Actually, in integral form, we may define these terms defined in equation A. You know it very well how the scalar product of two eigenvectors are defined in integral form. So, writing the scalar product scalar product in the integral form. The condition in A is, how we can write this condition defined in equation A in integral form. We will write it if we consider that the eigenfunction is one-dimensional. In that condition, in integral form, we will write it as integral minus infinity to plus infinity a hat psi 1 of x star psi 2 of x dx, and the RHS of equation A will be integral minus infinity to plus infinity psi 1 star of x A hat psi 2 of x dx. Say this is B. As I have written the first condition A, and this condition is same as defined in A, but it is in integral form. Actually, this scalar product defined in equation A or equation B is denoted by a particular symbol. This scalar product is written as Bra-Ket psi 1 A psi 2. In fact, the operator A is written between the two vertical lines. See here, the operator A hat is written between these two vertical lines, and on one side of A hat we have the first eigenket or first eigenfunction psi 1, and in another side is another eigenket or eigenfunction psi 2. This is just a symbol to write down such a scalar product in symbolic form. Now, this operator A, if it is Hermitian, then it may be attached with psi 1 and psi 2 both. Either with psi 1 or with psi 2, we can imagine it. If we consider that A is attached with psi 2, then if we assume A to be attached with psi 2 of x, then this symbol psi 1 A hat psi 2 will mean product of psi 1 with A hat psi 2. And this is alright, we can write it. And actually this is RHS RHS of A. This is RHS of equation A. And at the same time, A may be attached to psi 1. Or we can write psi 1 A hat psi 2 equal to A hat psi 1 psi 2. And this is nothing, this is simply LHS of A. But remember, if A is a Hermitian operator, then both of these are same. If A is Hermitian, then this will be equal to this. So, if A is Hermitian, we can imagine A to be attached with psi 2, and then after that we take its scalar product with psi 1, and on the other hand, we can attach A with psi 1 and then we take the scalar product of A psi 1 with psi 2. But result will be same if A is a Hermitian operator. Now we will see a very important property of Hermitian operator that you may note it. If A hat is Hermitian operator, if A hat is Hermitian operator, then one thing we must remember that psi 1 A hat psi 2 is equal to psi 2 A hat psi 1 star. This is a most important property of Hermitian operator. And you will see when we have to check any operator to the given operator is either Hermitian or not, we always check it. We find the LHS and RHS of this equation C, and if they are same, then we say that A is Hermitian. But how? Now we will prove this very important result. So first of all, we see the proof of this very important property of Hermitian operator. To prove this result, let us start with RHS of equation C. You may start with LHS, but here I am going to start with RHS of equation C, and you will see that this RHS is equal to this LHS. So what is RHS? RHS of this equation is psi 2 A hat psi 1 star, and in integral form, how we will define it? We will define it integral minus infinity to plus infinity A2 psi 2 of x star, this is complex conjugate, and psi 1 of x dx, and this is star. Here, as I have told above, that this operator A is if Hermitian, then we can associate A with psi 1 or psi 2. Here, I have associated this operator A with the function psi 2 of x. Now, what is this? this will be integral minus infinity to plus infinity, and this is a hat psi 2 of x and psi 1 star of x. See here this is complex conjugate of a to psi 2x, and we take again its complex conjugate. Then we know this will be the real value, and psi 1x complex conjugate will be psi 1 star of x. And now we will write it as integral minus infinity to plus infinity. First of all, write psi 1 star of x and a hat psi 2 of x dx. And by definition of the scalar product, what we will write it? We will write it, this is actually the scalar product of psi 1 with this much. And so I am just writing here, this will be actually equal to what? This is psi 1 a psi 2, and this is nothing but LHS of equation C. So we have seen that these two quantities are same, and as I have told you, this will be very beneficial when we will solve the problems based on Hermitian operator. So remember this property always. Now we will discuss the important properties of Hermitian operator. After knowing the definition and an important property or condition of Hermitian operator, now we are going to discuss some of its important properties. Some property I will prove, and some property I will give you just an information and hope you will prove them yourselves. So first of all, the most important property of a Hermitian operator is that the eigenvalues of Hermitian operators are real. So eigenvalues of Hermitian operators are real. This is a most important property of Hermitian operator. So eigenvalues of Hermitian operators are never imaginary, never complex, they will be always real. Now we will prove this very important property of Hermitian operator, that the eigenvalues of Hermitian operators are real. To prove this property, let us consider an eigenfunction, or you may say Eigenket phi, and a Hermitian operator A. So let A be a Hermitian operator. Hermitian operator, and Ket phi is an Eigenket or Eigenfunction. The eigenvalue equation is given as, we will write the eigenvalue equation of this operator. You know how we will write eigenvalue equation. Operate the operator on the given eigenket, you will get the eigenvalue of the operator and the same eigenket. Say it is equation 1. Here A is what? A is the eigenvalue of the operator A, which is a Hermitian operator. So A is equal to eigenvalue of A, and we have to prove that this A is real. It cannot be imaginary, not complex, but it will be always real. We want to prove it. And to prove this, let us take the scalar product of equation 1 with Ket phi. Take a scalar product of 1 with Ket phi. We get what we will get. We will get that, see here, if we take a scalar product of this with Ket phi, the result will be phi A hat phi, and this will be, as A is a number, complex number, so it will be outside of the scalar product. So this is A phi, Bra-Ket phi and phi. Say this is equation number 2. Now we have to prove that A is real always. So for this there will be some mathematical step. First of all, we take the complex conjugate of this equation 2. Taking complex conjugate of equation 2. So taking complex conjugate of 2. What we will get? We will get that phi A hat phi star, and this will be equal to A star Bra-Ket phi phi star. Say this is equation 3. But we know that we have already studied in linear vector space that this product of phi with phi, we know in integral form this will be integral minus infinity to plus infinity phi star of x phi of x dx, and this is simply integral minus infinity to plus infinity phi of x mod square dx. And so this is what? This is real and positive. And if it is real, it means this is real. And if this is real, then its complex conjugate will be same. So complex conjugate of product of phi with phi will be equal to product of phi with phi. And again, as A hat is Hermitian, and we have just now learned that if A is Hermitian, again as A is Hermitian, so psi 1 A hat psi 2 star, this equal to psi 2 A hat psi 1. We have just learned. And so in the light of this equation, what we can write this? So we can write product of phi A hat phi star equal to phi A hat phi. Now we will substitute these values, that is this and this, in equation 3. So in LHS, at the place of this much we will write this, and in RHS at the place of this much we will write this. So what we will get from equation 3? So equation 3 is now written as, how we will write equation 3? We will write it phi A hat phi equal to A star product of phi with phi. And what will be the equation number? This will be equation number 4. This is equation 4. Now see equation number 2 and equation number 4. You see that the LHS of equation number 2 and the LHS of equation number 4 are same, and so we can equate equation 2 and 4. So comparing two and 4, we get what we will get. We will get that A product of phi with phi is equal to A star product of phi with phi, and this is A minus A star product of phi with phi, and this is 0. But we know that this product is not 0, it is in fact real and positive, greater than 0. It is 0 only when phi is 0, but you know, if phi is 0, then it will be not a valid wave function or valid Eigenket. So we know this product phi of phi with phi is not equal to 0. And so what will be 0? then you may write A minus A star is 0, and this implies A star is equal to A. And if A star is equal to A, it means what? It means A is real. And what is A? We have assumed that A is the eigenvalue of the Hermitian operator A hat. So it is now proved that the eigenvalue of Hermitian operator is real. So eigenvalues of Hermitian operators are real. So this was a most important property of Hermitian operator. Now we will see another important property of Hermitian operator. The another important property of Hermitian operator is the eigenfunctions of a Hermitian operator corresponding to different eigenvalues are orthogonal to each other. This is also a very important property. So eigenfunctions, or you may say eigenkets of a Hermitian operator corresponding to different eigenvalues are orthogonal to each other. So if there are two eigenfunctions of a Hermitian operator, and corresponding to those two eigenfunctions there are two different eigenvalues, then those eigenfunctions will be definitely orthogonal to each other. So now let us prove this important property, and for proving this property we consider the two eigenfunctions or eigenkets of a Hermitian operator. So let ket phi 1 and ket phi 2 are two eigenfunctions of a Hermitian operator A hat with different eigenvalues A1 and A2. Remember, this word is very important. The eigenvalues should be different from one another. Then the eigenvalue equations are, what will be the eigenvalue equations? First equation will be A hat ket phi 1 is equal to A1 ket phi 1. This is equation 1. And the second eigenvalue equation will be A hat ket phi 2, and this will be what? This is A2 ket phi 2. These are the eigenvalue equations of the operator A hat. Remember one thing here, that this A1 and A2 are not equal. Here A1 and A2 are not equal. A1, A2 are not equal. In this condition, we have to find that these eigenfunctions ket phi 1 and ket phi 2 are orthogonal. And you know what is the condition for orthogonality. If phi 1 and phi 2 will be orthogonal, it means the scalar product of these phi 1 and phi 2 must be 0. So we have to prove what? We have to prove that the scalar product of phi 1 with phi 2 is equal to 0. We have to prove this. Now let us see how we will prove this very important result. So to prove this, we take the scalar product of each side of equation 1 with ket phi 2 and with ket phi 1 of equation 2. So taking a scalar product of each side of, see here, each side of 1 with each side of 1 with ket phi 2 and each side of 2 with ket phi 1. And after this we will get what we will get? We will get that, see that equation, phi 2a phi 1 and this product is equal to A1 product of phi 2 with phi 1. This is, say, equation 3. And after taking the product with ket phi 1 of equation 2, what we will get? We will get that this is phi 1 a hat phi 2, and this will be A2 product of phi 1 with phi 2. say this is equation 4. Now we take the complex conjugate of each side of equation number 3. So taking complex conjugate of each side of 3, what we will get? This will be complex conjugate of this product, and this is equal to A1 star complex conjugate of the product of phi 2 with phi 1. Say it is equation 5. But as we have studied in just now that if A is Hermitian operator, then what we can write this product? So we can write phi 2 A hat phi 1 star equal to phi 1 A hat phi 2. As we know, A is Hermitian, and as I have told you this very important property in very beginning during the definition of Hermitian operator. Again, phi 2 phi 1 star is equal to product of phi 1 with phi 2. Why? This is just the property of a scalar product. This is just, you may say, definition of a scalar product. Definition of a scalar product. Now, again we can write from the property of Hermitian operator that A1 star is equal to A1, because we have just read that the eigenvalues of Hermitian operators are real. So you may say as eigenvalues of Hermitian operator are real. And so using these results, what equation 5 will become? You see the equation number 5, and we will write, instead of this expression we will write this much. Instead of A1 star we will write A1, and instead of this much we will write this much. So now using these results, our equation 5 will become, what equation 5 will become? So 5 becomes, 5 will become the product phi 1 A hat phi 2 equal to A1 product of phi 1 with phi 2. This is equation 6. Now see equation number see here equation number 4. The LHS is this much, and you see that LHS of equation 6 is also same. So now we will compare this equation 4 with equation 6. So comparing with equation 4, we get, comparing with equation 4, we get A2 product of phi 1 with phi 2 equal to A1 product of phi 1 with phi 2, and this implies A2 minus A1 product of phi 1 with phi 2, and this is 0. But as I have just mentioned in the statement that the eigenvalues of the operator corresponding to the two eigenfunctions are not same, are different. So A1 is not equal to A2, and hence this factor is not 0. And if this factor is not 0, definitely this product will be 0. So therefore, what we will get? We will get that product of phi 1 and phi 2 is equal to 0. And this was to prove, as the product of these two eigenfunctions are, a scalar product of these two eigenfunctions are 0, so we can say that the ket phi 1 and ket phi 2 are orthogonal to each other. So this result implies that ket phi 1 and ket phi 2 are orthogonal to each other. So this very important property is also proved. So this is all for today. In next lecture we will discuss some other properties of Hermitian operators and some of the important problems based on it.